A-level further mathematics. We are going to consider complex numbers. If you found this video to be helpful, don't forget to share with your friends, and also do not forget to subscribe to my channel so that anytime I upload a new video, you'll be notified. You recall from quadratic equations that x squared plus 9 equals 0. This has no real roots. So this is how we go about it. We solve for x. Now we know that x squared, we know that there's no real number whose square will give us -9. So solving for this, we get x to be equal to the square root of plus or minus square root of -9. Now we know that we can separate this to a real part. That is, we can rewrite this as -1 times 9. Then we know that this is a real, the square root of 9 will give us a real number, so we split the sign for it. Now you know this will give us a real number, which is 3. Then the square root of a negative number is not real. Now since the square root of -1 does not exist, we need to define the root of -1. So if we let the root of -1 to be equal to I, then I squared will be -1. Hence the solution to this will be x equal plus or minus 3i, meaning that the solutions can only be imagined, they are not real. So you can see that the -1, root of -1, cannot be illustrated on the number line. It can be illustrated on the number line. So that is why we refer to it as imaginary. So this is -1. So root of -1 cannot be found over here, cannot be illustrated here. It can only be somewhere here, or we can imagine it up there. Now the general complex number is given by z equal x plus iy. So the one we just saw previously, it means the x is 0, that is -3i, and +3i, the x is 0, and the y is 3 or -3. Now these have the real part and it has the imaginary part. The y is called the imaginary part. And so for example, 2 plus 3i is a complex number, -3i is a complex number. So this is having a real part of 2 and an imaginary part of 3. And this is having only an imaginary part of -3i. So we have -1 minus I. Then we have 1. It's also a complex number. That is, it has the imaginary part to be 0. So this can be written as 1 plus 0i or 1 minus 0i. So this tells us that for all real numbers, they will belong to the set of complex numbers, or they are subsets of the complex numbers. So all real numbers are subsets of the complex numbers. So a complex number is just an extension of the real numbers. The modulus and argument of a complex number. Now we have the real axis, which is the x-axis, and we have the imaginary axis, which is the y-axis. Now we can represent complex number as coordinates that can be illustrated on a diagram. That is x and y coordinates that can be illustrated on a diagram like this. Then this complex number will have a modulus, which is r, and you remember that this r is the hypotenuse of this triangle over here. for that matter, we can define the Pythagoras theorem on this. So the modulus is equal to the square root of x squared plus y squared. Coming from the Pythagoras theorem, that is r squared is equal to y squared plus s squared. So the modulus OP is denoted by r. Now we have an angle that is formed with a positive x-axis over here, and that angle is called the argument or axis. So the argument of the complex number. So the axis is the argument of the complex number, and this is the mod z. So modulus of the complex number is r. Now we can find this using trigonometry. So we know that the tangent is defined by the opposite over the adjacent. So y over x. For x not equal 0, so that must be defined where x is not equal to 0. For x not equal 0. But if your x equals 0, then it does not define. It's not defined. Now this whole diagram, which is telling us the illustration of the complex number on the axis, that's the real, and the imaginary axis is called the argand diagram. The argand diagram. Now let's look at some few work examples with a complex number. Find the modulus and argument of the complex number 1 plus root 3i. Now the modulus is here over here. So to find the modulus is just using Pythagoras theorem, that is d squared plus d squared all square roots, and we simplify to get root 4. And root 4 will give us 2, so the modulus is 2 units. 2 units. Now we are asked to also find the argument, which is the theta over here, the angle theta over here. So the tangent is going to give us the y, which is the y over x. So we have root 3, the tan inverse of root 3. So theta will be equal to pi over 3. Now it is because theta is in the first quadrant. Theta is in the first quadrant. So theta is equal to pi over 3. Or, we know this is positive. So tangent is positive here and here. So it's supposed to be pi over 3 plus pi over 3. That will give us 4 pi over 3. So it's actually supposed to be equal to 4 pi over 3 or pi over 3. But you can see from the diagram that this is in the first quadrant. So the correct answer is supposed to be pi over 3. Now that's the first example. Let's take another one. We have this. We're finding the modulus and argument of the complex number root 2i minus root 2. So we can plot this, illustrate this on the Gantt diagram, as you can see. So this is the real part, this is the real part, and this is the imaginary part, which is root 2 units. Now someone can choose to indicate this as a modulus, which will give us root 2, and that approach is also different. But over here I'm taking it holistically from the real axis. So we measure it from the real axis. We are considering the angle from the real axis. So the tan theta is now the modulus of z is given by this squared plus this squared plus this squared. So simplify this to get 2 units again. Now we need to find the angle theta over here. Now this time we need to be very careful. So we know that tan theta is equal to root 2 over negative root 2. That is y over x. Now we simplify this to get tan inverse of negative 1. Now the tangent ratio is negative in the fourth and second quadrant. So you remember cast. All students take calculus. So tangent is only positive in the first and the third quadrant, but in the second and the fourth quadrant is negative. So theta is the tan inverse of negative 1. So it means theta is equal to either negative pi over 4, which will be in the third quadrant over here, which will be in the fourth quadrant over here. That is also the same as, we know this thing is the same as 2 pi minus pi over 4. So 2 pi minus pi over 4, 2 pi minus pi over 4, and that will give us what? 8 pi minus, so this will give us 7 pi over 4, which is over here, which is here. But that is not what we are looking for. We are looking for the angle over here. So negative pi over 4 is the angle over here, but 3 pi over 4 is the angle over here, and this is what we are looking for, because that is where the complex number is located. So we discard this and take this as our answer. Hence theta is equal to 3 pi over 4. So you need to be very careful when it is negative or positive. You should know where it lies. So our answer is 3 pi over 4. So our answer is 3 pi over 4. Now we are supposed to find the modulus and argument of the complex number negative I over 2. So this is how we illustrate this. Now we know that this can be worked out so simple. It's very simple. So the modulus is given by this 0 square. We know this, the real part is 0, imaginary part is negative 1 over 2, and this will give us 1 over 2 as the modulus of the complex number. So from here to here is the 1 over 2 as the modulus. Now you have to know that this complex number is coinciding with the imaginary axis. Now we need to calculate the argument. Now the argument is given by this. If you want to go by the formula, you see this is not defined because we have a division by 0 over here. Now we know that this over here is 270 degrees, or 3 pi on 2. So this will give us pi over 2, another pi over 2, another pi over 2. So you know the angle theta is given by pi over 2 plus pi over 2 plus pi over 2, and this will give us 3 pi on 2. It's over here. So it's not always that we go strictly according to the formula. The understanding is very important, especially when the complex number is coinciding with the axis. Now we find the modulus and argument of this complex number over here. Now this is how we illustrate this over here. So this is how we illustrate the Gann diagram. This is the Gann diagram for the complex number. So we find the modulus as usual. The x is x is negative root 3 and the y is negative 1. I've interchanged them over here. There's no effect on the answer, so we are going to get 2. Now we need to calculate the theta over here. So we know that theta is equal to y, which is negative 1 over x, which is negative root 3. Now we simplify this to get 1 over root 3. So the tan inverse of 1 over root 3 will give us pi on 6 or 7 pi on 6. 7 pi on 6. Now we know that the tangent is positive. This is positive in both first quadrant and the third quadrant. So we are looking for the one in the third quadrant. This is in the first quadrant. So our correct solution is in the third quadrant, which is 7 pi on 6. So that is the tidbits on how to calculate, and a simple way of doing that, straightforward. Now there's another way where you find the angle over here as the principal angle and add it to this, or subtract it to any of the quadrantal angles over here. Now the polar form of a complex number, polar coordinates, is just a matter of representing something in the form of modulus and an angle theta, or magnitude and an angle. So we have a complex number over here. That's the Gann diagram. Now from trigonometry, we know that cos theta will give us cos theta will be opposite adjacent over hypotenuse. We simplify to get x to equal r cos theta. Now similarly, we can find y to be equal to r sin theta. Then when we substitute into the complex number, we get z equal r cos theta plus I r sin theta. Factorizing the r out, we get cos theta plus I sin theta r, multiplying everything. So this is the polar coordinate form. So we know that the modulus is the mod z, which is the r, and the axis is the theta for us. Then we also know that we can also write this in the form r comma theta. That's polar coordinates for you. Now let's see how we can work with this. We are writing this in polar coordinate form. Now we've seen this already, and we found our modulus to be 2, and we found our theta to be equal to pi over 3. Now we just substitute this into the formula z equal r cos theta plus I sin theta to get 2 cos pi on 3 I sin pi on 3, and that is the polar coordinate form for you. If you like, you can write it in the form r comma theta. Now if you like this video, don't forget to subscribe to my channel and keep coming for more videos will be uploaded. The continuation will be uploaded very soon, so keep on coming. Wish you all the best.